Hello again, this is Mrs. Lusardi. In our previous lesson, we learned about Boyle's law, which explained the relationship between the pressure and volume of a gas. Today, we're going to move on to look at another of the gas laws called Charles' law, where we relate temperature and volume. If you do have the printed notes, this starts on page 4 of your notes. If you don't, whether you do or don't actually, please make sure you have a notebook handy where you can work through the sample problems with me. So in Boyle's law, we held temperature constant. Now we're going to look at what happens when temperature goes up or down. So when the temperature of a gas goes up, the molecules start moving faster and banging around more, and something's got to give. Either the volume has to go up, or the pressure has to go up, or in some cases, both will go up. But first, we're going to look at the individual relationships between temperature and volume, which is Charles' law, which I'm going to cover today, and then temperature and pressure, which is called Gay-Lussac's law, which I will cover in a future session. So Charles' law relates temperature and volume, and it says that at constant pressure, the volume of a fixed amount of gas is directly proportional to its Kelvin temperature. So directly proportional means that as one goes up, the other goes up. And another important note is it's the relationship between temperature in Kelvin. The relationship is not valid if we use the temperature in Celsius. So Charles' law applies when you have a flexible container such as a balloon. If I blow up a balloon inside in my house and it's nice and warm, and then I take it outside on a cold winter day, the air pressure inside and outside is the same. So when I lower the temperature and the molecules start moving slower, the volume of the balloon will decrease. If I then bring the balloon back inside, it will gradually warm up and the volume will increase back to its original volume. When we graph a direct relationship, it looks like this. So essentially, at 0, 0, this represents 0 on the Kelvin temperature scale, the lowest theoretically possible temperature where all motion of particles ceases. Theoretically, at absolute 0, there would be no space between the molecules, there would be no motion, and they would collapse into a little teeny tiny pile, which would occupy almost no volume. Then as we increase the temperature, the volume increases. So if I am here and I double the temperature, I double the volume. The equation that we use to relate volume and temperature is V1 over T1 equals V2 over T2. Again, V stands for volume, T stands for temperature, and the critical thing is the temperature must be in Kelvin. From an earlier lesson, we learned that if we know the temperature in Celsius, we can get Kelvin by adding 273. So here's an example. The pressure in this case is constant because there's a piston being held in place by air pressure. So as we heat up the molecules, they'll start moving faster, and that will cause the volume of the container to increase. So where we have a piston, where only atmospheric pressure is applied, or we have a balloon where atmospheric pressure is applied, if we increase the temperature, we will increase the volume. Again, I want to emphasize this volume-temperature relationship is not valid when temperature is expressed in degrees Celsius. So here's an example. I have a 2.5 liter balloon that I filled up in my house, and it's at 20 degrees Celsius. If I go to a warmer area where it is 40 degrees Celsius, what will be the new volume of that balloon? You may be tempted to say that since the temperature doubled, the volume doubled. But in reality, if you were to do that, you would see very little increase in volume because doubling the Celsius temperature does not double the volume. If we calculate this problem correctly, V1 over T1 equals V2 over T2 using temperature in Kelvin, the new volume is 2.67 liters. The volume increased only about 7% because the Kelvin temperature increased about 7%. So the key item here is whenever you use temperature at any time in any calculation in this chapter, it must be expressed in Kelvin. So I'm going to go through some examples of Charles' Law problems. I'm going to skip the one in your notes because that jumped right to a pretty difficult one that required a lot of manipulation. So I want to start with a relatively simple one. So again, whether you have the note packet or not, please have a separate piece of paper where you can actually learn to work through these problems with me. So in number one, I have a gas at a temperature of 300 Kelvin, and it occupies 6.5 liters. Note that both of these numbers have 3 sig. What if I change the temperature to 250? What will its volume be? So remember, this is a direct relationship. So as one goes up, the other goes up. As one goes down, the other goes down. In this case, my temperature is decreasing. So I would expect my volume to decrease. So I plug my values into my equation. For these types of equation, the easiest way to solve for x, or in this case V2, is to cross multiply. So I have cross multiplied. V2 times 300 K equals 6.50 liters times 250 K. To get V by itself, I divide both sides by 300 K. It cancels out on the left and shows up on the bottom on the right. So V2 equals 6.5 divided by 250 times 250, divided by 300. Put that into my calculator, and I get 5.42. My units of Kelvin cancel out. I'm left with a unit of liters, which is good because I'm trying to find volume. So all of my numbers in this equation have 3 sig. They're all Pacific numbers. They have 3 sig. Therefore, I express my answer with 3 sig. So that was a case where we were solving for the new volume. In the next case, I have a 1.24 liter volume of nitrogen at 285 Kelvin. What Kelvin temperature is required for it to expand to 2.48 liters? So my initial volume over my initial temperature, my new volume over T2. And when X or T2 is on the bottom, it's especially important to cross multiply. If you were to divide both sides by 2.48, that would not give you T2. That would give you 1 over T2. So please get used to cross multiplying. So this gives me T2 times 1.24 equals 2.48 times 285. Again, to get T2 by itself, I must divide both sides by 1.24. Cancels out. So T2 equals 2.48 times 285 divided by 1.24. Put that in your calculator, and you get 570 K. Note the point after the 570. My numbers have 3 sig, so my answer has to have 3 sig. Excuse me, if I did not have that point there, it would only have 2 sig, which would not be correct. Now, in both of these examples, I gave you the temperature in Kelvin, so you could just use the numbers as is. In example number 3, I gave you the initial temperature in Celsius, and I said, what volume would it occupy at 75 Kelvin? So you cannot plug 75 Celsius into the equation. you must change it to Kelvin, sorry. So 75 plus 273 gives me 348 Kelvin. Plug in my numbers. V1 over T1 in Kelvin equals V2 over 75 Kelvin. Now let's look at what's happening here. My initial temperature is 348. My new temperature is 75, which is not only lower, but much lower in temperature. So I would expect a much lower volume. So I'm going to cross multiply. I'm going to divide both sides by 348. So V2 equals 3.22 times 75 divided by 348. Notice from a volume of 3.22 liters, we went to a volume of 0.69 liters. Also notice when we look at our sig digits, I have 3, 75 only has 2, so I must round my answer to 2 significant digits. Okay, so these are the sample problems for Charles' Law. Tomorrow's assignment will be to solve problems using Charles' Law. So if you need to, you can refer back to this either from what you've written down in your notebook, or the same things are illustrated in the PowerPoint that's posted on Classroom. Okay, so tomorrow's will be homework on problems, and then we'll come back and review the temperature versus pressure relationship.